All right. Well, thanks everyone for joining. Welcome to the NSIDC Cryosphere Seminar. Today we have Alek Petty, who is an associate research scientist at NASA Goddard and the University of Maryland. And he specializes in polar sea ice variability and has been working a lot with ICESat-2 and IceBridge and on the science teams for those. PhD in climate science from University College London, and is now, as I mentioned, at NASA Goddard and the University of Maryland, and has done quite a bit of work and done some really great stuff on getting good sea data and sea ice thickness and sea ice freeboard data out of ICESat-2, which is just a key parameter in the Arctic sea ice. So Alek is going to talk about some of the new insights from ICESat-2. So Alek, take it away.
Cool. Yeah, thanks very much, Walt. My goal today is just to give you a bit of an overview of ICESat-2 with a focus on sea ice. As Walt said, that's my kind of speciality, but ICESat-2 does a bunch of other things beyond sea ice, which you should be aware of. So it's mostly work undertaken through the ICESat-2 Project Science Office, which I'm a member of with a bunch of others at NASA Goddard. And then, a bit of the work we've been doing with Rachel Tilling's science team project, trying to produce an all-season record of sea ice conditions from ICESat-2 and Cryosat-2. And then, some of the work as I've been doing as the kind of new data product lead for the ICESat-2 sea ice products. So, I took over from Ron Kwok just over a year or so ago. He was, pivotal in, coming up with all the algorithms for the sea ice products for ICESat-2 over the years prior to launch of ICESat-2. So his job was a lot harder than mine. But it's a fun task now to try and see how we can continue to improve and develop the sea ice products and expand our understanding of sea ice from this mission. My interests are maybe more broader than this specific mission, but I'm going to be focusing on this one aspect today. So if you want to find out more, my website, alekpetty.com, has some links to some other projects and papers too. And so I've kind of assumed that you guys are pretty well versed in the polar regions, with this being an NSIDC seminar series. As I said, I'm just going to talk about sea ice, the floating component of our cryosphere today. Putting these slides together, I realized it was pretty Arctic focused. That wasn't fully intentional. It just seems to be how these things can kind of play out. We are maybe more concerned with some of the changes we're seeing in the Arctic. So that tends to be where we look to first. And then for sea ice especially, there's some added complexities with some of the remote sensing challenges when we try and do similar things for the Southern Ocean and Antarctic sea ice and profiling. So my hope is that maybe in a year or two's time, we can give a similar talk showing some of the more Southern Ocean focused research we've been doing. But for now, I think it's mainly going to be looking at some of the Arctic results we've obtained. You're all very familiar with this graph, I'm sure. So this is the 40+ year record of sea ice area across the Arctic in black and the Antarctic in teal, using Walt and others NSIDC derived CDR product in the solid lines, and then the OCSAC in dashed. So this is the Arctic sea ice extent at the end of summer for both hemispheres. So we see that kind of halving of sea ice extent in the Arctic, and then the kind of more interesting, slight increase and then radical decrease in recent years for the Antarctic. As I said, I'm interested in these trends and what they mean for our climate system, but it's not a big part of my research currently. What I'm really interested in doing and helping with is this goal of moving beyond tracking sea ice area and providing more information about sea ice conditions in that third dimension. So sea ice thickness and also higher state information such as flow size, leak fraction, concentration, specific regimes, things like that. So there's a bunch of reasons why we want to do that. As Walt said, it's thickness for one is an important parameter, and there's various reasons as to why it is. Some of the motivation behind our work that's kind of playing on my mind right now is listed here. So we're part of another project right now called Polar Mirror, where we're trying to improve the representation of polar regions in climate models and the next generation NASA reanalysis system, which will be Mirror 3. And so part of that is thinking about how we can better represent sea ice within reanalysis systems, especially as we move towards fully coupled systems. Some of the work we've done recently has demonstrated clear biases in things like atmosphere energy fluxes of heat and moisture, which we really think a lot of that is due to the fact sea ice isn't fully represented in these systems. I think historically in weather models and especially atmospheric models, sea ice is often treated as a boundary condition. It's the presence of or lack of sea ice which modifies the surface fluxes. But I think plenty of research recently has shown that actually the sea ice conditions themselves also play an important role in modulating fluxes between the atmosphere and ocean. So yeah, our hope going forward in the next few years is to better include simulations of the assimilation of sea ice information into global models. Also, our lack of we need thickness to constrain volume. So thickness times area equals volume. And yeah, as I'll show in a couple of slides, in the next few slides, the lack of current volume constraints really hinders our ability to seasonally forecast sea ice and also project forward on decadal scales as well. But yeah, the big caveat is, this isn't because people are lazy and don't want to do it. The big problem is that we generally have had a lack of reliable basin scale sea ice thickness data available to do this kind of work. But we're hoping that's starting to change now. So, here's an example of where we're at. This is a figure of March on the left and September on the right sea ice area. The black or the dark gray is showing historical simulations from CNIP-6, and then the colors are showing different projections using different emission scenarios. These are figures actually from this SIMIP community paper led by Dirk Notz, but he was also the lead author for the cryosphere sections of the IPCC report and included these figures in a similar fashion there. And again, these were insightful figures showing an update of our ability to project forward in time sea ice conditions with the latest CNIP-6 ensemble suite, showing things like, in September, we fully expect now virtually an ice-free Arctic sometime in the middle of the coming century, unless we can, radically move on to one of these more ambitious emission scenarios, such as 1 to 2.6. But yeah, one of the key comments in, I think, the paper or maybe the IPCC report was this idea that for sea ice volume, we do not compare models with an observational estimate due to substantial uncertainties for reanalyzed and observed estimates of Arctic sea ice thickness and mass volume. So this was essentially the modeling community saying, we don't trust the thickness and volume observations yet to really use them to constrain or at least assess the projections that we're generating. So for context, the observations shown in black are those same CDR, I think, or maybe OTSAT, maybe what knows, passive microwave derived sea ice concentration data. So that's still kind of the only real baseline being used to constrain projections. And then, yeah, another figure, again, from the latest IPCC report. This is a figure generated by Ron Kwok, again, the former data product lead for ICESat-2 and a key figure in the kind of sea ice thickness world. So he's a contributing author to that IPCC report. And yeah, it put together this record of thickness change for the Arctic. Similar plots have appeared in some of his older papers. So this was a kind of more recent update with latest data. But really what this is, it's a bit of a patchwork record of thickness change, right? This is our kind of best effort at piecing together different platforms and sensors to look at how thickness has changed. So it's not that nice, routine passive microwave record that I showed you earlier. The beginning part of the record is this regression analysis of submarine data, upward-looking sonar measurements of draft, which are converted to thickness. In the 90s, we started to have some airborne surveys, EM surveys over the North Pole, helicopter surveys, I believe. Again, very limited in scope, but crucial for understanding and providing some additional data beyond the submarine record. And then it was the early 2000s when we started seeing the advent of this kind of really polar focused altimetry era. So ICESat launched in 2003 and ended in 2009. Then ESA's Cryosat-2 launched in 2010 and is still ongoing. IceBridge, shown by these points here, was a NASA airborne mission launched in 2009 to bridge the gap between the end of ICESat and the upcoming ICESat-2 mission, which launched in 2018. So yeah, this was a great effort by Ron, but yeah, there's plenty of issues here that I'm sure he'll be open to. You know, the IceBridge data is not updated all the way. ICESat-2 is kind of mentioned in this report, but it was too young then to be integrated into this assessment. The error estimates are pretty rough. You know, they're each kind of calculated for each sensor and then applied across the entire period of interest for each sensor. So yeah, I don't know if this assessment is really good enough to assess decadal trends, particularly. So this is kind of what is our baseline really to work forward on. And then, yeah, there's no equivalent plot at all for the Southern Ocean. So there's hardly any mention of Antarctic sea ice thickness in the IPCC report. So that's, you know, another big gap that we need to fill going forward. So part of the challenge is you know, measurements of sea ice thickness from remote sensing platforms are hard, right? The key thing is we don't measure sea ice thickness. We measure things like freeboard, and then we back out thickness. So this is my schematic of some of the various approaches to doing that and some of the challenges associated with remote sensing of sea ice in terms of altimetry and freeboard. So on the left, we've got kind of a typical scene in the winter, and on the right, a typical scene in summer. For laser profiling, such as ICESat and ICESat-2, we measure height of the ice surface, typically the snow-covered ice surface, and then also the leads between ice floes. So it's a difference in those height retrievals gives us an estimate of total freeboard. For radar, things like Cryosat-2, it's a bit more complicated. The radar is expected to penetrate down through the snow layer towards the snow ice interface instead to give us a measurement of ice freeboard. There's lots of things that can complicate that. There's, you know, melting of the snow, which can impact radar returns. There's a refreezing of that meltwater within snow layers, ice layers, which can further add to the complexity and the challenge. For laser, clouds can give us real problems and data dropout. Less of an issue, well, no, not an issue for radar. And then when we make this conversion from freeboard to thickness, we assume the ice is freely floating. We assume this hydrostatic equilibrium of our ice flows, but we know that in localized regions and coastal regions, we can have significant internal stresses which can complicate matters and reduce that or provide an added sense of uncertainty based on that approximation. Summer, we have added complexity from melt ponds, so similar to passive microwave challenges, it's hard to sometimes differentiate melt ponds on top of the ice from lead and open water openings next to the ice. But again, for freeboard calculations, that's a problem, right? Because the surface of a melt pond is going to be slightly different to the surface of the lead or sea surface. So yeah, as I said in a previous slide, there's been various missions that have been pieced together that have given us measurements of freeboard and thus thickness. And the new big fancy one that we're interested in is ICESat-2. So ICESat-2 launched in 2018. It launched in September 2018. Science quality data was obtained from the middle of October 2018 onwards. Yeah, it's a fantastic machine. The primary sensor on board is Atlas, this photon counting laser altimeter. Atlas uses this pretty novel 6-beam configuration shown in the middle here. It's this 3-beam pair setup, a strong and a weak beam for each beam pair. Mostly that was driven by needs of the ice sheet and ice shelf community. Understand, by having this kind of split beam configuration, you can calculate gradients and slopes, which are really vital for assessing biases when measuring elevation over fast changing terrain. For sea ice, it's maybe less essential. and we're still trying to figure out the exact benefits of that beam configuration. But at the very least, it increases our coverage significantly compared to a single beam. There's much better resolution, sampling, and precision than the preceding ICESat mission. This is a nice schematic on the right here showing ICESat beams in red, and then just one of the beam pairs from ICESat-2 in green. So much smaller footprints, better along track sampling, and also higher precision as well. And then ICESat also suffered from various issues. The big one was laser degradation. So it was quickly observed that the laser was degrading. And so they had to preserve the lifetime of the laser system and to enable a multi-year record from ICESat, they had to move it into this kind of campaign profiling operation. So they would collect data in kind of 6-week chunks and turn it off again to try and preserve the laser. ICESat-2 hasn't had any issues like that. The laser is performing still extremely well, hardly any degradation. And so really consistent science quality data has been obtained for just over 3 years now. The primary product from ICESat-2 is ATL3. So some of you here, I'm sure, are familiar with ATL3. It's a bit of a beast of a data set, which you guys have had to host and share with the community. I'm sure it takes up a lot of server space. Why it's so big is it's the geolocation of every single photon detected by ICESat-2 or Atlas. So, just a small cross-section of ATL3 is shown at the bottom schematic here, made by Marco Bagnardi. So, every green dot here is a ATL3 geolocated photon. And what's cool is when you just plot it raw like this, you see things, right? You see the surface. The idea is we have signal photons and background photons. The Atlas detects green laser light at a very specific frequency, the same frequency as that's emitted by ICESat-2. So we'd expect to receive a lot of signal photons where we have a surface and those laser returns bounce off of. But we also get a lot of background photons too. The sun has some photons emitting at a similar energy level, and backscattering of other sources of radiation can trigger background photons to be detected too. So that's what's shown by the green dots either side of that surface. So it's an extremely challenging data set to use because it just gives us data everywhere. But it's a pretty cool one to work with and look at as well. So the real goal of ICESat-2 in the Project Science Office was to then derive higher level products beyond ATL3, which made the life of the end user much easier. The key one being finding those signal or surface photons and getting rid of all those background photons that we don't really want when doing science. The approach taken has been very different for different domains. So there's a sea ice, set of data sets. There's an ice sheet set of data sets, a vegetation set of data sets, because we all have kind of different expectations of where that surface is and how we should go about deriving a surface elevation data set. So this is what the basics of what the first ATL7 sea ice height product does. Again, I'm just going to really skip over the details here, but there's an ATBD and a user guide on the NSIDC portal if you want to find out more. The first thing it does is essentially carry out a lot of surface windowing. So for the polar oceans where we expect to see sea ice, we know roughly what the mean sea surface is, right? We've been able to track that with other altimetry missions. And in general, we expect that surface to vary, within plus or minus half a meter or a meter beyond that sea surface. So that's kind of our first guess at where those signal surface photons are coming from. That gets rid of a lot of the noise for us and really narrows things down. A bunch of other filters are then applied, and then the kind of main step is this application of a Gaussian, which to the remaining photons aggregated within these given sections. So the algorithm developed uses aggregations of 150 photons along each beam and fits a Gaussian. It's actually a complicated double mixed Gaussian, but I won't go into those details today. Here's 4 examples of that Gaussian fitting in action over different types of surfaces. The 2 on the left during the day, so we have background photons. The 2 on the right are actually at night, so there's no background. But the 2 on the right seem to be coming from rougher surfaces, right? Those Gaussians are wider than the 2 on the left. So the Gaussian fitting gives us kind of a mean height, but also some kind of proxy for roughness and uncertainty too. and allows us to further filter out noise as well. So this is another schematic showing what happens there. ATL3 on the top. We have these footprints that are like 11 meters by 11 meters that have an, pretty high uncertainty, around 20 centimeters. The idea is that we want to beat that precision or that uncertainty down by aggregating photons, right? We assume those errors are randomly distributed. So if we aggregate those photons, we can beat the noise down. That's why this 150 photon aggregation was chosen, because that gives us an expected precision of around 2 centimeters. And some of the validation of the flat surfaces highlighted that is what we're kind of seeing, which is great. So the cost of doing that is that we had this slightly bigger footprint compared to ATL3. And because we aggregate photons, and photon rate can vary, we have this kind of interesting data set, which is a variable resolution, a long track data set. So the actual size of these footprints can vary along the beams as our reflectance changes over different surfaces. So something to consider. As I said, for sea ice, the key is really differentiating ice from open ocean or leads, because then we difference those heights to derive freeboard. So again, there's kind of a complicated algorithm that Ron developed to do that kind of radiometric classification. The key things it uses are the photon rate, the Gaussian fit that I talked about earlier, and also the background rate to essentially figure out what might be a lead versus might be ice. The key ones we look for that are pretty common is high photon rate, smooth, narrow Gaussians with low background, and they're what we classify as a specular lead. So you can think of those as kind of mirror-like surfaces, very flat, open water surfaces between ice where the wind isn't causing much roughening, and we have, essentially a mirror that laser signal is bouncing off of, and we can be confident that those are leads and not ice. So the sea ice products are being validated in various ways. That the height and freeboards from ATL 7 and 10 have been compared with estimates obtained by Operation Icebridge. I mentioned that earlier. That was Operation Icebridge just ended. It was an airborne campaign over the polar regions. A bunch of different sensors on board to measure various things, but also a laser altimeter similar to ICESat-2 that can give us freeboard and height. So there are 4 underflights of ICESat-2 that Icebridge undertook in spring of 2019, which was a really fantastic group effort to try and nail down when and where those underflights should occur, and to fly this plane along a path that we expect those ICESat-2 beams to profile. And this was very successful. So there was 4 good underflights obtained by Icebridge, and Ron produced some really cool comparisons between the 2 data. Again, 2 independent data sets collected of heights. So these 4 comparisons are shown here. ICESat-2 in black, Icebridge's ATM sensor in red. These had to be kind of optimized because the ice has moved. There was some time difference between the 2 data profiles, but by maximizing the correlation, we try and account for that drift and that offsetting. And so when you do that, you produce these 2 profiles here, and the match between the 2 was really fantastic and great to see. So very high correlations and low errors. Freeboard differences were slightly more significant. The other thing we're trying to do. Can we mute that maybe?
Someone mute your line.
Great. Thanks, Will. The height retrieval seem to be performing really, really well. The other thing we've been looking at in the PSO is how are that classification procedures working, because again, that's a key part of this. And this has been a really fun exercise. So we've, mostly Marco, our support scientist, has been hard at work finding coincident imagery that we can compare to, because part of the problem with ICESat-2 is that we don't have an image of the surface that we're profiling. We have to just trust the single laser system. So we have found some coincident scenes from Sentinel-2. Sentinel-2 is a really high resolution imager, 10 meter resolution or so pixels. Here's a nice example that was found. The time separation between ICESat-2 and Sentinel-2 was around 3 hours, and there was a slight offset, which Marco's corrected for here. And when you do that, you see things line up really nicely. So red is where ICESat-2 is classifying the surface as ice. Yellow is where it's classifying it as those specular, shiny leads. And we can see that lines up really, really nicely with the image here. So we see these kind of big openings here, just to the lower part of the image across all 3 beams. These are just the strong beams. And then we're even picking out these leads in these very small cracks that are only tens of meters wide, which again is one of the big benefits of ICESat-2's really high resolution system, that we can pick out not just the big leads, but the small leads too, which existing missions we think probably struggled with, although we're still looking into that. Just to show that in a different perspective, this is just one of those beams now overlaid on a similar Sentinel-2 image, this one just north of the Canadian Arctic archipelago. And again, yeah, just really, really nice to see. We're picking out the big lead opening here, and also the smaller cracks here. And this matches up really well with the drops in reflectance from Sentinel-2. So again, this was really cool to see, because not only does it give us confidence in our ability to pick out the leads, but it means we can start doing kind of more novel things like estimate lead fraction, lead length, chord length, which is essentially the transect across the flow, which again is a very new and exciting avenue for sea ice research. Putting that all together, we can then deduce freeboards. So again, use those lead heights, compare those to the ice heights, do some more fancy calculations, and you can back out freeboard, which is what's given in 10, which is shown at the bottom here. So yeah, low freeboards, where we have the leads, obviously, that should be basically 0. And then higher freeboards for the ice-covered regions. And what's nice is if you zoom in on these images, you can see ridge features over the ice flows too, which the freeboards coincide with as well. Just a qualitative assessment that things seem to be working well there too. Here's what those distributions look like across the entire Arctic. So we're now pretty confident on those freeboards and kind of running with it. This is some of the first data we collected and analyzed from ICESat-2. This is all the data collected over winter 2018 to 2019, split it up by regions using one of the classic NSIDC region masks. So the nice thing here was that we saw really similar freeboard distributions in the Eastern Arctic first-year ice regime. So the Chukchi, Siberian, Laptev, and Kara Sea shown here. So they're all around 20 centimeters or so in the mean with similar distributions. And then, wider, bigger freeboards in the multi-year ice pack of the Central Arctic. So that was all using the second release of ICESat-2 data and published last year. Things get more interesting in summer, as I mentioned earlier. This is some work that Rachel Tilling is leading as part of our efforts in the Project Science Office, looking at ICESat-2 over summer sea ice. So as I said, ICESat-2 is producing data all the time, even over summer ice. Things are just more uncertain. So, data users should just be more wary of how they interpret the data in summer. This is some work she's been doing, looking at things like leads versus melt ponds. It's kind of hard to see. There's a lot of information here. Maybe it's better to save that for another talk. But essentially, we see kind of similar specular returns over melt ponds as well as the leads, which is a problem. And yeah, there's different types of melt ponds too. Some are drained, some aren't, some are rough, some smooth. So this is kind of an ongoing challenge as we try and do better freeboard estimations in summer. Yeah, if we go back to that decision tree I showed earlier, essentially it means anything could be a melt pond. It's really the height filter that we have that can kind of tell us how to use them for freeboard. So another thing we're doing is, as I said, ICESat-2 is performing really well at picking out leads and giving us those sea surface height estimates. So then because of that, we can use those lead surface measurements to tell us about the polar sea surface height variability. So similar work was done with Cryosat-2 with some colleagues at CPOM a few years ago. And we're trying to extend that with ICESat-2, see how well ICESat-2 does at tracking sea surface height variability across both polar oceans. And again, this is some work that Marco Bagnardi led and published on earlier this year. The really cool thing was that this work was benefited by the fact as of August of last year, ESA actually altered the orbit of Cryosat-2 to increase the coincidence with ICESat-2. So now every 20 orbits from ICESat-2 is broadly semi-synchronous or coincident with Cryosat-2. So now we very frequently see these nice transects across the ocean, which are kind of shown by these lines here, which are almost exactly coincident with Cryosat-2. So then we can produce these coincident profiles shown on the right here. So these are 4 examples where we're showing sea surface height, essentially the height from just those lead points, binned over kind of 10-kilometer sections across the Arctic Ocean. ICESat-2 in red, Cryosat-2 in blue. And yeah, we can see these match extremely well, which is nice. So they're showing kind of similar magnitude and similar along track variability as well, giving us confidence we can use ICESat-2 to also track polar sea surface variability. Yeah, and then Marco kind of put this all together and, you know, gridded them up and looked at what the entire Arctic Ocean sea surface height looked like. And yeah, this was nice because we could see key features that we expected and hoped to see, such as, you know, the doming of the sea surface height in the Beaufort Gyre region. Again, similar to what Cryosat-2 picks up. Yeah, Marco's kind of hard at work looking at this and extending this. Part of the challenge now is we have these 3 beams, the 3 strong beams, and they're still not giving us exactly the same results. So our hope was that by now we could kind of use all the beams together to look at sea surface variability, but there's still work ongoing to kind of fully align and reconcile the heights we're getting across the beams, but currently we're having to treat them all independently. Another cool thing is looking at waves. So this is some work mainly that Chris Horvat's been leading as part of his science team involvement. Again, ICESat-2 gives us really high resolution height estimates within the polar ocean. So we can start looking at leads and how those heights within the leads and around the leads are varying. Chris did some cool work looking at, you know, where we'd expect to see waves and how the height signal is changing with ICESat-2 and calculating a wave activity map, which is really nice. See his paper for more information. We also looked at just some, yeah, again, some of the coincident imagery from Sentinel-2. And yeah, I really liked this profile. So I think this kind of further demonstrates the capabilities of ICESat-2. So again, here are the beams from ICESat-2 on the left here. If you just pick this one beam and plot a profile, we see some really cool things. So we see, again, these kind of big lead openings. That's what the blue horizontal lines are showing, which kind of match up here. We see some kind of height variability here from this kind of milky ice. But we actually see some kind of significant variability within the leads and also within the ice cover as well, which you think are driven by kind of small scale wave activity too. So this was fun to see. And then we could also see some interesting oceanographic features like this increase in the sea surface height towards the coast. So this kind of coastal dynamic ocean topography signal that we know, does exist around coastal Antarctica and helps drive this kind of coastal current, which was, again, cool to see from the raw data. Oh, that should move. The other thing we're trying to do is, move beyond the official products and derive estimates of sea ice thickness. So this isn't really part of the official data product release from ICESat-2, because to go from freeboard to thickness, we need to start introducing a lot more data that isn't primarily produced from ICESat-2 itself. So I showed the schematic earlier. We're measuring total freeboard from ICESat-2, but to derive thickness, we need estimates of the snow depth and density, the ice density, the water density, that assumption of hydrostatic equilibrium. And all of those assumptions introduce errors. But we're proceeding anyway. Prior to the launch of ICESat-2, we developed a simple snow on sea ice model in NESOSIM that we're using to try and back out the snow contribution to that total freeboard that we're measuring from ICESat-2. We recently updated NESOSIM to a newer version, calibrating that with some of the new measurements we obtained from IceBridge. And yeah, this seems to be working pretty well. So this is some of the results we showed in our original paper. We have the ICESat-2 freeboards at the top from ATL10 from one of the beams. Again, maybe picking out some of the ridges here that we can see and highlight the variability we can estimate with ICESat-2. The middle plot is showing the snow depth from our models. So NESOSIM is actually shown in this black line. It's kind of a static value at this small scale, but we do some redistribution of that large scale snow to the high-scale ICESat-2 using some relationships obtained from Operation Icebridge. And then below is showing our kind of resultant thickness using different input assumptions. So again, there's a broad agreement in what the thickness looks like using different assumptions, but there's still significant uncertainty between these estimates. So, we can measure thickness, but the uncertainties are typically high, order of 20 or 50% or so. Yeah, there are newer methods for trying to derive this all concurrently, just using satellite data. Ron Kwok's led some of that work, looking at measuring snow, using Cryosat-2 and ICESat-2 together to do snow and freeboard and then thickness, but that's still very much preliminary work. I'm not going to talk as much about today. So this is some of the first data we collected from ICESat-2 in October of 2018, which I presented at the first science team meeting, which was very exciting. And yeah, this was cool because we observed this regional distribution in freeboard on the left, which made sense to us based on our understanding of sea ice. The NESOSIM snow in the middle here from our reconstruction or model, and then our resultant estimate of sea ice thickness. Yeah, so this was all very encouraging to see, and the seasonal evolution through that first winter also made a lot of sense to us, which was nice. We now, as I said, have 3 winters of data, which is cool. So this is some more preliminary work that we've just been undertaking to assess how the thickness, or the freeboard from ICESat-2, the snow depth from NESOSIM, and the thickness has changed through these past 3 winters. Yeah, I worked a bit with Walt on using this for the NOAA Arctic report card as well to kind of, track how thickness is changing from one year to the next. So here we can see some interesting things with the freeboard over these past 3 winters, that you can kind of eyeball it and see there's been a bit of a decline in freeboard perhaps, especially along the coast of the archipelago. But we see some interesting regional patterns in that difference. Here's what NESOSIM, our snow depth, shows, and there's again some significant variability there from one year to the next. So maybe higher snow in that first winter, lower snow in the middle, and kind of increased again in the previous winter. Again, we do expect snow to vary a lot from one year to the next, which is why we need to use these models, not just use a simple constant, which previous missions have had to rely on. And then this is kind of the resultant sea ice thickness, bringing this all through. So yeah, the first winter on the left, the middle is the second winter, the right is the most recent winter. Hard to really track the changes there, so let's just plot these finally on a time series. So this is just taking the data within a kind of inner Arctic domain across these past 3 winters. We're showing freeboard on the top left, snow depth on the top right, and the resultant thickness at the bottom. The shading represents our uncertainty. So yeah, it does seem like ICESat-2 has tracked this pretty consistent decline in freeboard over this just 3-year period. But interestingly, our NESOSIM snow depths are also showing a decline. So when you incorporate a decline in freeboard, but also a decline in snow depth, that kind of reduces the impact on sea ice thickness change over this time period too. So yeah, our results, our preliminary results, are suggesting there's been maybe a slight decline in the winter sea ice thickness in this past winter compared to the previous 2. But by the end of winter, actually, the decreases in snow offset the decrease in freeboard. So it's actually pretty similar. We're seeing kind of mean thicknesses of around 1.8 to 1.9 meters or so. Yeah, and this is all using the derived gridded monthly thickness data that's now disseminated through the NSIDC. So next, guys. Yeah, I think I'm running out of time. So just to summarize on the ICESat-2 work, ICESat-2 heights, ATL7 and freeboard ATL10 just really look good. Obviously, we need to do more validation work. We need to assess things like the ridges, the real small scale features, and how well ICESat-2 is picking those out. How well we're capturing and calculating the heights of all those leads. If we have some biases, some studies are suggesting there might be some little tweaks we need to make. Summer data still poses a big challenge. We're trying to extract new information, beyond the basic mission requirements of ICESat-2, such as the lead length, fraction, and flow size. Comparing and hopefully reconciling with other missions like Cryosat-2. ICESat-2 also looks to be a great platform for tracking polar sea surface height variability. As I said, the beams across ICESat-2 are still not fully aligned. We're getting slightly different results, which isn't ideal, so we need to work on that. And yeah, if you notice, our maps are all limited to the ice cover. There's a separate open ocean product, and so you know, how they calculate a sea surface is slightly different to how we calculate sea surface. So we need to reconcile those, which is work ongoing. Then yeah, I'm more principally interested with this question of sea ice thickness and updating those estimates of snow and thickness. But again, they'll hopefully be better constrained and validated with some of the new data that's been collected by moorings and some other airborne campaigns too, and Mosaic and other things. So yeah, a lot of this data is now disseminated through the NSIDC. So thanks again to some of the people that might be on this call that have helped with all that work. That's been really appreciated. Yeah, so 5 or so ICESat-2 sea ice products. Yeah, one of the things to highlight is that there's a kind of latency here with ICESat-2 of something like 45 to 60 days. Most of that is driven by the need to obtain precise geolocation orbit parameters. There's been a strong demand for a rapid product with, you know, less precise geolocation determination, and that's been pushed for a while, and that actually is all been approved and should be being posted through, I think, the NSIDC in the next few days, I believe. So that's going to be exciting to see, and hopefully increase the utility of ICESat-2 for more kind of nowcasting activities going forward. I think I'm kind of out of time. I just wanted to like pose a couple of slides just to maybe get people thinking in different ways beyond what I just showed here. Is that okay, Mistia? Have I got 2 more minutes?
I think, yeah, a couple more minutes is good.
Great. So yeah, I think one of the points I want to make is we're collecting all this fantastic data from ICESat-2, and I think, you know, for me, the next big challenge and frontier is how we use all this data. You know, a lot of the results I'm showing and other results I've shown before, you know, we tend to, I don't know, work with these data in our ways we used to. We're gridding them and assessing changes, but maybe this isn't the best way of doing it. I think there are, you know, more sophisticated means of assimilating some of those observations into models to create, you know, sea ice or even global reanalyses. And I think that's, you know, it's going to be some of the exciting work going forward over the next few years. We're going to need some tweaks to some of the models, perhaps, for us to enable that assimilation of information, new, you know, prognostic flow size distributions, new emulations, and I think there's a lot of exciting work on that front. And then, yeah, there's still a need for more sea ice observations. So ICESat-2 doesn't give us everything. We need other data sets to either validate what we get from ICESat-2 or to expand it into more derived variables. I think we can maybe make better use of the existing satellite missions we have, and also other data sets, such as those upward-looking sonar drafts that I think are really crucially underused. And yeah, I think there's a lot of exciting work ahead with UAVs and UUVs to provide additional insights beyond what our satellites are giving us now. And then finally, yeah, there's a bunch of exciting missions coming up. ICESat-2, we're hoping will carry on for several years. It's, you know, it had a nominal 3-year mission period, which those reviews are expected to happen at the beginning of next year. But yeah, the health of ICESat-2 is extremely good, and the expectation is it will keep giving us data for many years to come, and hopefully the funding will follow that to enable us to continue working on and tweaking the data we're producing. But there are a bunch of other missions coming up too that we're interested in. ARC-6 is a dual aircraft mission for monitoring summer atmosphere and sea ice conditions, which will be cool to see. There's the SWAT mission, which is due for launch late next year, which is this kind of interesting wide swath radar interferometer system. NISA launching in 2023, a kind of different type of L-band SAR mission, which will tell us things about, you know, high scale, high resolution motion and deformation. And then, yeah, planning is underway to think about what comes next, you know, on a kind of more 10-year horizon, you know, an ICESat-3 like mission perhaps, and what that might look like. So yeah, thank you very much for listening.